Hello, this is Professor Kuehn, and this will hopefully be my last lecture on Chapter 8 of A Student's Guide to the Great Physics Texts, Volume 2. Remember what had just happened. Salviati, speaking for Galileo, had just presented his theory of falling objects, that is, that they undergo uniformly accelerated motion. He had fielded some objections by Segredo and Simplicio, much to their satisfaction, and now he summarizes his perspective. He says, a motion, this is at the top of page 114, a motion is said to be equally or uniformly accelerated when, starting from rest, its momentum receives equal increments in equal times. Notice once again that he's using the terms momentum and speed and velocity interchangeably. Later on with the work of Newton, we're going to see that the term momentum is used slightly differently. It's used as the product of mass and velocity. But Galileo is using those terms interchangeably because he's sort of developing the science and there's not a settled terminology yet. So when he uses the word momentum, you might think of just the quickness or the speed or the velocity. Okay, so that's a summary of what he's developed up until this point. And now what he does, he goes on to explain a couple of implications of this. He says, consider this sketch showing a ramp. The vertical height of the ramp is denoted by the line segment CB, and there are two different paths. In fact, these are two ramps with different slopes. One slope is represented by the line segment CD, the other slope is represented by the line segment CA. And he makes a claim here. He calls it an assumption. He says, if you were to have a body at the top at point C, and you were to let it slide down the ramp CD, by the bottom it would have a certain speed or velocity. If, on the other hand, you were to take it at C and let it slide down a different ramp, it would go down ramp CA, it would get to the bottom with a certain velocity as well. And here's the claim that he makes. The velocity is going to be the same regardless of which ramp it slides down, as long as they're both sliding from the same height, an altitude CB. It doesn't matter the path they take, they will have the same velocity by the time they get to the bottom. Now, he doesn't prove this here mathematically. That's something we'll do later on in the semester. He simply makes this claim. And then when he's questioned by Segredo and Simplicio about how he knows this to be true, he gives an explanation for why he thinks it's true, and he uses a different experiment to explain that. So if you jump ahead a page, to page 115, he gives an argument for why he thinks that these objects sliding down different slope ramps arrive at the bottom with the same speed. So how does he explain this? In figure 8.3, he depicts the following situation. He says, imagine you have a board and you have a nail sticking out of the wall at point A. And then you have a string that is hanging down and there's a ball hanging at point B. Okay? If you were to pull this ball back and let it swing, it would swing along the arc CD. So if, for example, you were to pull this ball back along this arc like this, and so it's up at this point right here, point C, so that the string is this way. If you release it, it will swing back along from C to B, and then it will continue by its inertia to rise up, and it will get up to point D. So here it is like that, and so that's the string once it's gotten to its maximum height over there. Now, I know that there is some wind resistance or some drag that will prevent it from getting all the way to the exact same height that it had been at, but it's going to get pretty close to the same height. So if I draw a horizontal line DC along there, it indicates the fact that if I release it at point C, it swings up to point D, which is just about the same height. Okay, now where does he go from here? He says, well, let's suppose now that we were to pull it back to point C, and while you were holding it at point C, you were to take another nail and you were to place that nail right here at point, I guess he calls that point E. If you were to do this, and now you were to let this swing forward, it swings forward, and when it hits, the string will hit point E, and then the ball will continue up along a slightly different arc. So let me make this arc blue. So it'll swing down like this, and it will swing up, and he says that it will get up to the exact same height if you were to do this experiment. That is, it will swing up along a different arc and end up at point G. But the important point is that it gets up to the same height. You can do this experiment. He says this is what you will find. And then he says, well, we could do the same experiment once again. We could pull it back to point C. We could put a nail over here instead at point F and repeat the experiment. It will once again swing down along this arc. The string will intersect the nail at point F. And then, lo and behold, what will happen? I'll make this one green. It will swing up like this. And once again, it will arrive at the exact same height, but it will go along a different path. So in the first case, with no nail at E or F, it swung up to point D. In the second case, with a nail at point E, it swings up to G. And in the third case, with the nail at point F, it swings up to point, I guess he calls that point I. Okay? Now, Who cares? Why is he doing this? What does it matter? Well, he says this is analogous to the ramp. If you think about this, instead of the ball swinging from C up to D, or C up to G, or C up to I, you were to think about it going in the opposite direction. That is, from D back down to B, or from G back down to B, or from I back down to B. That corresponds to the 3 different ramps of different slopes. And here's the more salient point, is that if the ball starts at point C and it swings down, in all those cases, it has the exact same velocity at point B, and that velocity will carry it up to point D in one case, to point G in the second case, and point I in the third case. So if you reverse that, going back down, if it starts at D and swings down, it will have a certain velocity at point B. Or if you were to start it at G and it were to swing down, it would have the exact same velocity at point B. Or if you were to start it at point A and let it swing down, it would have the same velocity at point B. So regardless of the steepness of the arc, you might say, the steepness of the arc along which the swinging ball descends, it will arrive at the bottom, that is point B, with the same speed. Okay, and he says this is analogous to balls or blocks or objects traveling down ramps of different slopes. That is, if they start from the same height, or they start at the same altitude, they will arrive at the bottom with the same speed. The bottom with the same speed. Now, does this prove that he's right? Well, that's debatable. After all, this is a swinging pendulum. The other one is an object sliding down the ramp. So they're not the same situation, but they're similar, and he means this to be a plausibility argument rather than a proof. Later on, we will see that in fact one can demonstrate that this is the case, but he does not do that yet. In any case, Segredo, at the bottom of page 150, chimes in right away and says, the argument you've just provided seems to me so conclusive and the experiment so well adapted to establish the hypothesis that we may indeed consider it as demonstrated.